Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to Learning by Solving Problem Session 8 on NMR. Deduce the structure of C6H10 that gives rise to the IR proton carbon 13 NMR and mass spec shown below. Be sure to show your thought process. Well, the first step, calculation of unsaturation number C plus 1 minus half X minus N. 6 for carbon plus 1 half monovalent element X 10 hydrogen makes the unsaturation of 2. As we know, unsaturation of 1 means double bond or ring. If you have 2 unsaturation number, mean that you have 2 double bond or 2 ring, or 1 double bond, 1 ring, or 1 triple bond. From the IR, we have here peak at 3311, very sharp, strong peak. Another one sharp but medium at 2120 centi-1. This indicates that you have carbon triple bond H terminal alkyne. So you have SBH stretch and carbon triple bond stretch. Also, we have here very strong peaks below 3000, which means that you have a lot of sp3ch bonds for CH stretch. Proton NMR shows triplet, sextet, quintet, triplet with very small coupling constant, and here triplet of doublets. We can summarize that at 0.90 we have triplet, J constant around 7.1 Hertz for 3 protons. This means that we have CH3 adjacent to CH2. Remember the rule 2Ni plus 1, I for proton half. So it turned out the equation to be N plus 1. We have here 2 hydrogens plus 1. So these protons, CH3 protons, will show up as a triplet. Now we have another peak, sextet, at 1.38, again coupling constant 7.1 for 2 protons. Sextet means that you have the 2 protons surrounded by 5 protons. So we have here CH2 surrounded by CH3 and CH2. At 1.47 you have quintet. We have here quintet for 2 protons, J value around 7.1. Well, you have CH2 surrounded by 4 protons plus 1 makes the quintet. We have 1.88 triplet and 2.14 triplet of doublets. J value for the triplet, it's 2.6. So this is not J3. It might be J4, we will be sure in a minute. For 1 proton, remember from the IR we have terminal alkyne. So if this is the case, we have here terminal proton showed up triplet. Okay, through the triple bond, we have coupling between this CH2 and this hydrogen, J4. Okay, that's assumption 1. Here now we have CH2. Adjacent to CH2, it will show up triplet. And with this one will be triplet of doublets. Well, sound good. To measure the J value between this in hertz, it's 2.65. For the triplet of doublets, again here is the same value, and the J value from CH2 is 7.1. We have C6 H10. This makes C2 H. We have C6 H10. So we have C4 left residue H9. We have CH3 CH2 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 makes 4, right? So we have CH3 CH2 CH2 CH2, that makes C4 H9. There is no symmetry in the molecule. That's why we are seeing it's 1, 2, 3, 4, 5, 6 signals. This is the solvent signals, chloroform. Okay? For the proposed structure as hex 1N, this carbon is 68.6, and we are seeing it at 67.9. Here is 83.7, here is 84.4. This one is 18, we have one in 18. This one is 30. We have 30.5, 21.5, 21.7, 13.2. Here we are 13.4, matching well. So the structure is hex 1N. Let's see the mass spec. We have here very small peak for the molecular ion as expected for alkyne, especially the terminal alkyne. Here is 81. Loss of hydrogen. Either we lose this H or one of these hydrogens to form 81. We can get McLafferty rearrangement and to give C4H6 peak at 54. We can also get peak at 43, C3H7. We can lose CH3 to get peak at 67, M over E. We can lose C3H4, cut in here, to get peak at 41, 41, 43, 55, 67. We can also lose C3H6 and we get this species at 39. Alright? But remember that in alkyne, a triple bond can migrate through the skeleton. And it's not easy to actually distinguish between different isomers, okay, using mass spec. Okay, but it's clear that we can confirm the structure as hex 1N from the mass spec, but the secure structure came from IR proton carbon. See you next session.